5.9 Approximate Integration. So there are two situations in which it is impossible to find the exact value of a definite integral. One, we may not know an antiderivative of the given function that we want to take the antiderivative of. Or two, the function may be determined from a scientific experiment through instrument readings or collected data. In such cases, we need to find approximate values of definite integrals. So all I'm saying in that second case is I have data instead of an actual function. We already know one such method, since any Riemann sum serves as an approximation to the integral. Specifically, the left and right endpoint approximations are illustrated on the next slide. So we've learned how to do in figure A, we have left endpoint approximation of the area under the curve, and in figure B, we have a right endpoint approximation. We also learned the midpoint rule. We chose an xi bar, which was right in between the left and the right endpoint, and that was our midpoint. And so we were able to use the midpoint rule also. So now we're going to learn the trapezoidal rule. And what the trapezoidal rule does is instead of creating a rectangle underneath, you're going to create a trapezoid, and you're going to just add up the areas of those trapezoids. Okay, this is one of the trapezoids that we want. And remember that the area of a trapezoid is the average of the bases times the height. Because usually in a rectangle you have base times height, but here we don't have a uniform base, so we do 1/2 of the base 1 plus the base 2, which is just the average base times the height. And so this trapezoid that we have here, we're going to look at it sideways, because this is actually my base 1 and this is my base 2. And this is my height. So you know that your height is just delta x. Now what is your base 1? Your base 1 we said was this. And isn't that length just f of x sub 0? So that's f of x sub 0 plus f of x sub 1 all over 2, because this height here is f of x sub 1, right? And so pretty much then I would take my next one, and my next trapezoid here would be the area. I'm going to just say T2, my second trapezoid, is you're going to average this one times delta x, right? And so you'll see that I basically have, that's how I arrive at this formula, because I'm only taking one of these since it's on the end, but this f of x sub 1 is getting counted in this trapezoid and in this trapezoid. Now you do not need to understand, you need to understand the formula. You don't need to use a formula because I just think it out every time. I just add up all the trapezoids, and you'll see that in the next example. You know, this is a lot of notation, which I know a lot of you are still uncomfortable with, and you're getting more comfortable with it. But in the next example, I think it's going to really make sense. So let's move to it. Okay, so let's try and use the trapezoidal rule to approximate this integral. So, of course, I'm going to use my number line. I'm trying to go from 1 to 2, and I need to split that into 5 trapezoids. So my delta x is just going to be 2 minus 1 over 5. I want to split it into 5 different trapezoids, and so I get 1/5. Okay, and so my trapezoids are just going to say, let me, remember that the area of a trapezoid is the average of the bases times the height. You know the height in this case is delta x. Remember your trapezoids are all kind of like leaning over. So I want to do a trapezoidal approximation with 5 trapezoids. Just going to abbreviate it T5 just like I was doing before. And so my first trapezoid is just the average of the bases. So the first one would be f of 1 plus f of 6/5 over 2 times the height plus the second one. So here's T1, basically, the first trapezoid, and here's the second trapezoid. Here's the third trapezoid. I would use those two. The fourth trapezoid, and then the fifth trapezoid. Would use those. So now that you see this kind of thing, you can see very clearly why in this formula you used 1 and then 2 of the f of x sub 1 and 2. So you use 2 of all the middle ones and then 1 again of the end. So hopefully that's making a little more sense now. But again, I just multiply all these rectangles and then, trapezoids, and then add them all up. I don't use that formula. Hopefully you're factoring the 1/5 out, but I'm not even doing that here. I'm just going to do dot, 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 because you would just do, 7/5 plus 8/5 in the next one, then 8/5 plus 9/5 in the next one, and the last one that you use is f of 9/5 plus f of 2. And so if you go ahead and just do that in your calculator, hopefully you'll take the 1/5 out and then you'll do your y1 thing. You should get 0.6956. So I want all of you to practice that on your own, especially since I didn't write it all out, and let me know in class if you have any questions with that. And then for the second part, the midpoint, I just need to go in the middle. So just rewrite my number line. So the midpoints are going to be not simplified, but that's okay. So here's my first, second, third, fourth, fifth. And so hopefully you're getting the hang of being able to factor out a common width, which you can't always do because sometimes our widths aren't equal, but here they are. And so you would have done the first rectangle would have been using the 11/10. So basically this would have been the width and that would have been the height. (15 over 10). Since I didn't simplify it before, I won't simplify it this time, so you won't get confused. And you should get approximately 691 Okay? And let's see how close we really are, because this one I can actually take the integral of. What is the antiderivative of 1 over x? Remember, it's ln absolute value of x. And we want to evaluate that between 1 and 2. So we get ln 2 minus ln 1, and that comes out to 0.6931. So you see here, both are really close. And so if you just look at a picture in the next slide, you'll see this is the trapezoidal rule, and here is using the midpoint rule, and both of them end up giving us a really, really good approximation. Even though it looks like the trapezoidal is going to do a lot better, the midpoint actually did pretty well in this case. And that's it for this lesson.